Until now, quantum computers have operated without their own dedicated memory. Unlike a traditional processor, a quantum processor cannot simply request data from standard random access memory, or RAM, to solve useful problems, such as searching massive databases. But having that memory is absolutely essential if we ever want to deploy quantum computers for real-world problems and practically harness their extraordinary capabilities. However, this is beginning to change. Researchers at Zhejiang University in China have built the world's first quantum random access memory, or qRAM, operating on a superconducting quantum processor, successfully testing it with capacities of 4-bit and 8-bit. Today on Technoverse, we are going to dive deep into this new qRAM prototype, how it works, and its promising future. Let's explore. This memory is not like traditional RAM. Because a quantum computer uses qubits to process data, it cannot directly interact with classical binary data, those standard zeros and ones, stored in conventional ways. Instead, it needs a method to represent this data as qubits, or superposed quantum states, to preserve quantum parallelism. This parallelism is a defining feature of quantum computing, allowing it to test multiple paths and solutions simultaneously. This new memory does exactly that. According to the study published in Nature Physics, researchers designed the qRAM based on a bucket brigade architecture. Memory addresses are accessed through a binary tree structure, similar to a decision tree made up of quantum routers. These routers direct queries coming from the processor through branching paths to locate and retrieve the binary information efficiently and, crucially, simultaneously. Here is where it gets really interesting. The memory does not receive a query for a single specific address like traditional memory does, where a classical processor sends an address to instantly get its corresponding value. The addresses coming from the quantum processor are in a state of superposition, meaning it sends a single query encompassing multiple addresses at once. In turn, the memory does not just return a set of values, it creates a precise quantum entanglement between each stored value and its associated address, returning them to the processor as a single quantum state. Of course, this imposes immense physical challenges. Linking binary values to qubits and then maintaining that entanglement while quantum states travel through buses to the processor exposes the system to environmental noise. This leads to numerous errors that can make information retrieval less than fully reliable. However, the team largely overcame these issues. They invented a new method to reduce the depth of the quantum circuit, introduced error mitigation techniques, and relied on an uncomputing mechanism to cancel out unnecessary entanglement with internal memory paths, which prevents the quantum state from collapsing. They tested two systems, a 4-bit and an 8-bit version. The system achieved a query fidelity of about 81% in the 4-bit system, but this fidelity dropped to 60% in the 8-bit system. This illustrates exactly how quickly errors accumulate when memory size increases due to the complexity of query paths, increased circuit depth, and the higher likelihood of fragile states interfering. This error rate is unacceptable for practical applications. If retrieval fidelity is low, the quantum processor will receive distorted data that does not reflect true values. The ultimate result is that the quantum waves will not interfere correctly during processing, and upon final measurement, the processor will yield a wrong answer instead of the correct solution to the problem. Therefore, this achievement is not a plug-and-play memory ready to work immediately with a quantum processor to solve real problems. Rather, it is a proof of concept. Commercial applications will need access to millions or billions of data points, requiring solutions to scaling issues, drastic reductions in retrieval errors, and hardware development to maintain qubit stability. So, Why is this achievement important? Historically, qRAM was merely a theoretical concept, the existence of which many quantum algorithms, such as search and AI algorithms, assumed as a prerequisite to be executed in reality. This achievement serves as a tangible, foundational step telling the world. The technology works in the lab. Now we need to figure out how to make it larger and less error-prone so we can start using it. If researchers and scientists succeed in scaling up this memory in the future, it will become the cornerstone for revolutionary applications, such as pharmaceutical research, efficiently analyzing massive molecular databases to discover and develop new drugs. The financial sector, scanning enormous high-speed transaction records to detect fraud patterns and suspicious activity. Artificial intelligence, improving the access of quantum AI systems to large datasets used in machine learning, natural language processing, and image recognition. If you are excited about the future of quantum computing, make sure to hit that subscribe button, drop your thoughts on qRAM in the comments below, and share this video with your fellow tech enthusiasts.